We hear you.
Hey guys, so from this week onwards, no more pre-lesson videos and welcome to post-lesson videos.
So what we're going to do in the post-lesson video is to summarize whatever that we've covered in the lesson earlier, and then we're going to use this content to build onto the next lesson for us, right? So what we're going to do over here is we're going to summarize things in a separate piece of paper. So you can just take out any piece of paper, right? And then we're going to go through together the new concepts, and we're going to summarize everything that we've learned. Okay, so today's lesson is going to be on reaction kinetics. So maybe we'll start off, Mr. Tim, can you share with me, right, which aspect of the chemical reaction am I looking at now if we talk about the idea of kinetics?
Well, we're looking at how fast the reaction goes, so rate of reaction. Yeah.
Sure. So let's take a look at a typical generic reaction. A plus 2B give me C.
Okay.
And if let's say I want to take a look at how fast a reaction is, one of the ways is to take a look at how fast my reactants are being consumed.
Yep.
So mathematically speaking, we're going to take a look at the idea of differentiation. So we can take a look at D, concentration of A against T, right? So that is differentiating your concentration of A against T. Now, this is a very mathematical concept, so let's take a look at a graphical manner. We're going to plot the graph of a reactant against time. So, Mr. Tim, reactant against time, do you think is an upward or a downward sloping graph?
Well, reactants get consumed over time, right? So the concentration should decrease. It should be a downward sloping.
Sure. So we're going to draw a curve that is downward sloping.
Let's go.
And we're going to take a look at this thing called the instantaneous rate. So let's say I want to find out the rate at time t1. What we're going to do is we're going to draw a tangent at a particular point t1, right? And we are going to measure its gradient. We can calculate its gradient over there. That gradient will correspond to the rate of the reaction. Now, what happens if I want to look at this thing called the initial rate then, Mr. Tim?
Okay, then if that's the case, then I need to make my T1 basically 0. Okay.
Right? So we're going to take a look at the point where T is 0, and we are going to measure the same thing. We're going to draw the tangent and go and find out the gradient as well.
Okay, beautiful stuff.
Now, one of the important things that we're going to look at is this thing called the rate equation, okay, which is a more mathematical way of expressing the rate. So, an example of a rate equation is given here, right? Mr. Tim, can you share with me, right? If I look at this rate equation, very clearly I can see what is the rate dependent on and what is the obvious thing there.
Yeah, you can see that your rate is affected by the concentrations of A and the concentration of B, right?
Which happens to be the reactants of the reaction, right? So, one of the things that you notice is, I think the rate, sometimes it could be more dependent on one reactant than the other.
Yeah.
How is it represented in this rate equation then?
Well, you need to look at the powers that the concentration is raised to, right?
Right.
And the larger this power is, the more it affects the rate of reaction, right? So in chemistry, we call this the orders of reaction. So we would say the order of reaction with respect to A is X, and the order of reaction with respect to B is Y.
That's right. Now, there's one thing called the overall order. And what is that, Mr. Tim?
So the overall order is just the sum of the orders, right? So the overall order is just X plus Y.
That's right. Now, one very important thing that you must remember is that this X and Y are not related to the stoichiometry. Only with one exception that I'm going to tell you later on. But in general, X and Y are always determined experimentally. And of course, later in today's video, we're going to show you how this is being done. Okay? Now, the next part of the rate equation, we have this very special letter K over here. This is known as the rate constant. And this rate constant depends on two major factors. Mr. Tim, what are they?
Well, we can recall from Sec 4, right? What affects your rate? It was temperature, it was catalyst. So your K is actually affected by temperature as well. The larger the K is, right? Sorry, excuse me. The larger the temperature is, the larger the rate constant will be.
Right.
And the lower the activation energy, the larger the rate constant will be as well.
That's right.
Okay.
So if you talk about your Sec 4 stuff, what are the factors affecting the rate? And they are all seen inside this equation, right? You have things like temperature, the presence of a catalyst, which lowers activation energy, as well as the concentration of the reactants. And they are all represented by this rate equation very nicely. Right?
Perfect.
Now, one of the things that you need to do as a skill is to figure out what are the units for K. Right? Mr. Tim, can you run us through how do we find the units?
So this will not be very simple, but remember guys, the units on the left must always equate to the units on the right. So the units for rate here, if you look at this formula, or how we determine rate, it is concentration of A over time, right? The change in concentration of A over time. So the units for rate here will basically be mole per dm³ per second, or seconds inverse, okay? So on the same thing on the right hand side, the units on the left must equate to the units on the right. And if you look at this with me, the units of concentrations of A and B will just be mole per dm³. And since they're both raised to the powers of X plus Y, sorry, X and Y, and they're multiplied together, this will just be raised to the order of to the power of X plus Y, all right? So the units of K here, I'm just going to put this in red. The units of K here will basically be mole per dm³ per second. divided, right, by mole per dm cube raised to the power of x plus y, okay? So units of K, square bracket means units in physics. Units of K will be mole per dm cube per second, let's go, divided by mole per dm cube raised to the power of x plus y.
So essentially what you're doing is making K the subject of the formula, and to do that as well, you're going to make the units divide each other as well, right? Okay, great. So you realize that this x plus y actually corresponds to the overall order of the reaction. Yep. So that's it. Okay, so this is the main general ideas of the rate equation. Now, the next thing that we're going to do over here is going to be finding out the orders of a reaction. So that is the next important skill we're going to do. And more often than not, exam questions love to give you a table of information. So we're going to illustrate this using an example over here. Let's take a look at this question over here. Now this question shows me not only just the initial concentrations of A and B, they also give me the initial rate. And this information is sufficient for me to deduce the rate equation, right? So we're going to run through the method over here. The first of which is going to be the inspection method. Mr. Tim, can you run us through this?
Yeah, sure. So first things first, guys. Look at these three experiments here. If you want to find the order of reaction with respect to B, then you need to make sure that the concentration of A is kept fixed. Now, Mr. Long, can you tell me which two experiments do that?
For A to be the same, it will be experiments 1 and 2.
All right. So what I'm going to do now with you guys is I'm going to do the inspection method, right? As the name suggests, we're not going to do any math, just inspect, all right? We just look. So as the concentration of B increases by a factor of 2, right? How does it affect my rate? My rate increases by a factor
of 4.
Let's go, right? And we know from simple math, 4 is just 2 to the power of 2, okay? So this tells me that when my concentration of B increases by a factor of 2, my rate increases by 2 square. So that square tells you that the order of reaction with respect to B is simply 2.
Wow, this eyeball method is really fast.
Powerful.
Yes. So let's find the order of A then.
Sure. So wait, to find the order with respect to A, then I need to keep B fixed, but I don't see that.
Right, so therefore we cannot use the eyeball method, we cannot use the inspection method, we have to use this new thing called the mathematical method.
Okay.
So how do you do that, Mr. Tim then?
Well, to do the mathematical method, what we're going to do is we're going to write rate equations for the experiments that we choose, and it doesn't matter which experiment you choose, up to you. So for this example, I'm just going to choose experiment 1 and experiment 4, okay? So you can see what I've did here. I'm going to write out the rate equation for experiment 1 and experiment 4. Just bear in mind, you already know the order of reaction with respect to B, which was simply 2, okay? So I have these two rate equations simply written out, and remember guys, bear in mind, your end goal is to find the order of reaction now with respect to A, which is basically M, all right? Now, Mr. Leong, how do I get rid of K?
So I think this is going to be a set of simultaneous equations. The easiest way is to divide the two equations together.
Okay. So the moment you just divide them, so you can imagine, just divide them across, and of course, because K is the same, the K, you simply just cancel off each other, and you can find M. Now, so from here, you just do your math, type in your calculator, and my mental power will help me out. M equals to 1.
Oh, wow. Well done, Mr. Tim. Very good mental power, indeed.
Thank you. Okay, and that's it, right? So this is where we have the inspection method and the mathematical method. So from here, we can conclude the order with respect to A is 1, the order with respect to B is 2. So my rate equation will be a very simple rate, let's go guys, equals to K, A, raised to the power of 1, which is the order, right? And B, raised to the power of 2. And that's it.
That's nice. So this is one of the very typical questions, and you have to be very proficient at this method. So what happens if the question gives you time instead? Mr. Tim, what would you do?
Wow, if it's time, I'm so uncomfortable with time, right? I will try to make it look like rate instead.
Okay.
So guys, we saw this in class. If the question focuses on product, right? Then if I were you, I would make another column here to kind of reflect rate, okay? And guys, remember, if the question is focusing on product, then your rate is just proportional to 1 over t. So in exam, I would do this. I will make another column, 1 over t. So 1 over 36, 1 over 36, and 1 over 9. All right? And then from here, I'll do the normal way. Again, inspection method, if you wish. If you want to find the order with respect to P, right, then you must make sure that Q is kept fixed. So choose experiments 2, experiments 3, as P times 2. How does your rate change, okay? So again, this is how you do it. Do not focus on the time. Do not use this column. If you do that, you are dead. Okay?
So the reason why we use 1 over time is also because of the differentiation concept, right? You do notice that rate is actually the same thing, proportional to your dAdt, so you can actually see that rate is inversely proportional to time. So that's why we use this method. But one very important thing that Mr. Tim has pointed out is the fact that you have to know what is the time measuring, right? If you're measuring the amount of time for the product to be formed, then you can use 1 over t. But sometimes the questions is a bit tricky. They like to give you how the time for the reactant to really disappear.
Yep.
And if that's the case, we are still saying that the rate is inversely proportional to time, but there's an additional concentration of the reactant factor, right? So therefore, not only the rate is inversely proportional to time, you must also put in the numerator the concentration of the reactant that you're trying to measure as well. Right? So therefore, once again, same thing as what Mr. Tim has done. For this question, you have to create another column, which is going to be concentration of the reactant against the time. So you're going to do that for the two of the tables over here, for the two experiments over here, and then following which, you just apply either your inspection method or your mathematical method to find out the rate equation. So once again, if you try to do that using time directly, you're going to fail miserably. Okay? That's it. So hopefully this is a good recap of our first lesson. We'll see you in class this week. See you guys. Bye.
We hear you.
Wait, one more time. You just, alright guys, you said we hear you first, right? Okay. We hear you. 1, 2, 3. We hear you. Next week, can I do a real mistake?
Yeah, I think